Hey again, Mr. Allred is still alive, and here we're going to talk about the limit comparison test to see if a series converges or diverges. So basically what we want to do here is we've got a series A, okay, and we're trying to determine if it converges or diverges. Well, we're going to take a series that we already know something about, B, and we're going to create a ratio of those terms and take the limit as we go to infinity. So think about what I'm saying here. In theory, a sub 1 would be over b sub 1. Excuse me, b sub 1. A sub 2 would be over b sub 2. So we're taking two matching terms in the two sequences, and we are creating a fraction. So we're going to do that for every term. Okay? So we're going to infinity. So basically what we're doing is we're looking at what this fraction does as we keep moving out. So now it says the limit is greater than 0. What this really should say is if the limit is positive and it exists, meaning if the limit is a positive real number, not going to infinity, not flipping around, not being negative or anything like that, but actually a number. So if this limit was 2, then we would know that these things had a very nice ratio as we kept writing the fractions out. And if that was true, that means that one is somewhat a multiple or a portion of the other. So if the ratio between these two was 2, okay, if we knew B converged, then we'd know A was always twice B. But B is getting infinitely small if the series converges, so even though A might be twice the size of it, it's getting infinitely small as well. So they have to do the same thing. Okay, so if B converges and this limit gives us a real number, then A also converges. Likewise, let's say it's still 2. Say that limit is still 2. If B diverged, then that means B doesn't have a sum. Well, if A is twice as much as B, then A doesn't have a sum either. And we're taking a limit, so some suggestions are, if you've got the limit of a rational function, you could use L'Hopital's rule. You could use those things that deal with the rational functions like the horizontal asymptote. You could use any of the rules that we already have for limits. But what we're talking about is how these two things interact. So if this thing is not positive, it tells you nothing. If the limit goes to infinity or is actually 0, then it tells you nothing. Because if the limit is 0, we don't know if the top is getting small or if the bottom is getting big. Okay, we don't know really what the difference between the two if we get 0 is. So just try and think about that. Okay, so it must give you a number back for this to have any type of conclusion, and you have to pick something that you already know if it converges or diverges. So if you're trying to figure out what A does and you have no way to figure out what B does, doesn't prove a thing. Okay? Well, we'll tell you they do the same thing, but that doesn't help. So let's see here. Let's get down to an example or two. So here, these problems are in the book, and these are the solutions manual, so they might not be exactly as you're expecting. But what we're trying to figure out is what A sub n does. So they've already created the fraction here. So A sub n, which is the sequence or series, n minus 2 over n cubed minus n squared plus 3. And we don't know what that does. That's what we're trying to determine. But we're going to compare it to 1 over n squared. And 1 over n squared is a p series exponent is 2. So this thing here converges. We know the bottom converges. So we're going to play with this limit, and we're going to do a little algebra to see if we can figure out what happens. So we've got a fraction on the bottom. We can keep change flip. So the n squared would end up on top of the fraction. We distribute it. So basically now we see an n cubed polynomial over an n cubed polynomial. So rational function, horizontal asymptote, would tell us that these are both cubes, so we could just look at this as being 1 over 1, or you could use L'Hopital's rule a couple of times, and you get down to derivative, 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 6 over 6, which is 1. So the ratio between these two series turns out to be 1 if you just keep writing the terms out. So basically, if you take the first term of each series, they might look very different. The second term, they might not look much more alike. The third term, still maybe not. But they're getting more and more alike. And if you write enough of them out, they pretty much start looking the same. So basically, if you go to infinity, they're the same series. So they might not have the same sum because they didn't have the same terms starting out, but eventually they look very similar. So that means they're both getting small eventually. So this is a real number, it's 1. We know the denominator converges, B converges. So that forces A to converge here. Okay. Let's jump to, let's see here. Let's do number 12. So what have we got here? We're trying to determine if 2 to the n over 3 plus 4 to the n converges or diverges. Okay. And we're going to compare it to 1 over 2 to the n. We can think about 1 over 2 to the n. It could be written as 1/2 to the n, so it's a geometric series. And that 1/2, that ratio in the geometric series, if we rewrote it, 1/2 is less than 1. Okay, so it's a geometric series where the rate or the ratio is less than 1, so that means it converges. We could actually find the sum of this thing. Okay, but we're going to use it as a denominator, so our B converges. So if we play around with this thing, once again, we're going to do some keep, change, flip. So we got 4 to the n on top and 4 to the n on bottom. Now there's a plus 3 on the bottom. Excuse me. But that plus 3 doesn't really do much as 4 to the n gets really big. So they might be 3 apart, but 3 apart between 1,000,000 and 1,000,003 is pretty insignificant. And then if you went to 1,000,000,000 over 1,000,003, it's even more insignificant. Okay, but you can also use the derivative, L'Hopital's rule. Once again, this thing turns out to be 1. That's just coincidence. So it's the same as the first one. Don't always expect that. But it gives you the real number 1. You knew the denominator, which we called B, converges. So now that we got a real positive number out of the limit, we know that the A function that we were given converges. Let's see if I've got one that diverges. Okay, so number 13 diverges. Let's roll it up here. So let's use this as our last example. So going down here, because this came out of the book, we're trying to figure out the series 5 to the n over the square root of n times 4 to the n, whether that converges or diverges. Well, 5 to the n over 4 to the n definitely looks like it's going to diverge because it looks like a geometric series. If you throw out the square root of n, you'd have 5/4 to the n, which the ratio is bigger than 1, so that would make it a geometric series that diverges. But we have something extra on the bottom, so we don't know how much that's affecting how large it gets or how quick it gets large. So we're going to have to compare it to something else. They decided to compare it to 1 over the square root of n, which once again is a p-series, 1 over n to the 1/2, and that exponent is less than 1, so it diverges. You could also prove it diverges by the integral test. But the thing that we choose for B diverges. So we do a keep, change, flip, and the square root of n's cancel out. And now we do have that geometric series with the ratio being bigger than 1. So these numbers are getting bigger in the sequence, so the series has a infinite sum. It just keeps getting larger, so we don't have a bound on that sum. So the limit did not exist here, or it did not give you a real number. So in that case, what we've got is we've got a divergent on the bottom. It keeps getting bigger. So the only way this thing could keep getting bigger, if the bottom diverged, the top would have to be bigger than the bottom. So it has to diverge as well. So that means that the given, what we would call A, also diverges. Okay, let me know if you have any questions. I hit pause.